So we begin the presentation.
Yeah, go ahead.
All right. So basically today I would just want to sort of like cover the last part of the introductory of error correction. So this part I will just cover the syndrome and the error correction part. So just a little bit of recap. So basically in classical error correction, a code word means that it is a vector C in such a way that you try to encode your message vector, which is given by M, with some parity check vectors. So in this case, if let's say the M vector is k times 1 kind of vector, so then the parity check is n minus k times 1 kind of vector. So usually there are sort of like n minus k parity check conditions. So these kind of conditions, when you if you treat them as column vectors, so you transpose it, you can write it into a matrix. So then you can condense all these parity check conditions into equation 2. So it's just a matrix multiplication in this case. So the multiplication requires you that when you multiply them, you get 0. So last time we also mentioned that if let's say we fix a basis for the code words, whereby your mj is basically coming from your message vector and bj is your basis, then a code word can be written into something like this. So basically is your basis now becomes the column vectors of a matrix G, and then your code word basically is just your matrix G multiplied with the vector n. So because of equation 2, so you can put equation 4 into equation 2. So you get this kind of conditions. So basically over here, you can also sort of like find the transpose of this part of equation and then define the dual codes for some codes that you already have. And then we also discuss about the minimum distance, which is given by, okay, I think there is some typo over here. It should be like this. It should be the CC dash, and then only you close the bracket equals to this. So what does it mean is that basically if you have two code words, the minimum distance is just covered by your Hamming weight. So this Hamming weight basically means if let's say you have two code words, you just find the difference between the code words and then find the minimum distance. So for example, if you have 000 and 111 as your code words, so basically your minimum distance will be 3 because 111 minus 000, you still get 111. And then for the Hamming weight, you just calculate how many ones occurring in your code words, which is 3. So after we get the minimum distance, we usually define a code in this kind of notation. So you state your n, k, and d. So d is your minimum distance. So a code of this form, you can correct up to the flow function of d minus 1 divided by 2 kind of errors. So in this case, if you have a repetition code, 313 code, so meaning that you have one bit and then you repeat it 3 times. So the minimum distance is 3. So if you compute the flow function, basically it will give you 1. So a repetition code can correct up to 1 errors. So this was covered last 2 or 3 talks ago. So now, what is error syndrome? So basically, if you have a code word that we want to transmit, so that is given by C. And then during the whole transmission process, when we receive the code by itself, which is given by Y, error may occur. So if let's say there's errors, so usually the errors would be Y minus C, which is the vector E. That that is if let's say we know what the original message is, then only we can find out what is the error in equation 7. However, we usually don't have information of C. So what we have is the receive vector, and then we need to try to guess what is errors. So the syndrome is uh, given by the kind of parity checks that have, whereby this hash is this original hash, and then we only have the receive vector y. So the syndrome is basically just the multiplication of hash with your vector y. So over here, you can really see that hash is basically a mapping of uh, f dimension n to n minus k. So if your y is basically coming from the code words, then basically your syndrome will be a zero vector because you don't need to fix anything. So it also means that the kernel of this mapping basically is the whole code word by itself. And the other fact is that because this Fn, vector power of n, basically is a group under the vector addition. So we can start to try defining the quotient group. Coset kernel, which is the code word by itself, the set of all code words by itself. It's just given by some vector adding to the code word by itself. And this actually partition the whole vector space as this. So basically you have the original code word, and then you union with some vectors, which we call as the coset letters, and then you union different coset letters and until it becomes the whole F2M.
So is that F2N?
Oh, sorry, it's FN2.
Okay.
Sorry, it should be FN2. Okay, I need to correct it. Okay, so so this kind of partitions is what we call as a standard array for the code word C. And how do we choose the coset letter? Usually the coset letter is chosen with the minimum handling rate. But if let's say in a particular concept, the minimum handling rate is you have multiples of minimum handling rates, then you just choose a random vector. So as I said before, because this is an abelian group under is also a normal subgroup, so that's why you can divide, you can define the quotient subgroup, the quotient group for all this. So then this fn minus k, it will be just the quotient group. Sorry, this should be n over 2, n and then 2. So there's a one-to-one correspondence between the concept, the error syndromes. So later on, we see one example for this. So because of all these kind of mathematical structures, uh, it actually allows us to decode the errors by using maximum likelihood. Because your errors, your syndrome, and then your receive vector, they basically belong to the same concept. Uh, the only thing that we need to take care of is how many errors that you can correct by this floor function. So now we look at one example. So this is a 633 code. So meaning that the first 3 bits, they are the message vectors. And then the last 3 bits, they are the parity check bits. So because we have 3 bits of message, if you look at the first 3 bits accordingly, you see that they will basically cover from 000 to 111. And then the parity check matrix is given by this. So this kind of code, because it's 3, so if you compute the flow function just now, basically you can only correct up to 1 error. So now we look at the standard array for this code. So if we try to compute the error syndrome, which is h multiplied by vectors over here, because the first row over here basically is the code words. So the error syndrome is of course 000. So then you try to compute all the possible cosets, and you find that different cosets basically they correspond to different error syndromes, right? So let's say, for example, this is the kind of vector that we want to transmit. Okay. So if let's say somehow at the middle, so this bit got an error, so it was flipped to 0. So it was flipped to here. So this is the one that we receive. So this is the coset leader. So the first column basically is a coset leader, because as you can see, let's say for example this particular coset. So the smallest Hamming weight is this, which is 1. So that's why this is a coset leader. And then if you can see, for example, this coset, basically you have multiple minimum Hamming weight kind of vectors. So this is Hamming weight 2. This is also Hamming weight 2. This is also Hamming weight 2. So in this case, you just pick 1 as your coset leader. Okay. So if let's say over here some error occurred in such a way that it flipped one of the bits over here to 0. So in this case, if you try to compute this by meaning you do hash multiply with this, so you find the error syndrome to be 010. So in this case, what you do is to use your receive vector. Adding or minus is doesn't matter, because it's just it's either 0 and 1. So let's say you add this concept leader, then you will get back your original message. So that's how the error correction for this kind of code actually works. But this code can only correct 1 errors. So for example, now you have 2 errors. So meaning these 2 bits, they are flipped to 1 to become 111111. So you have 2 errors. If you compute the syndrome, you get 111. So supposedly, you add these 2 vectors, you will get back the original message. But in this case, you don't get back to the original message, because what you're trying to fix is 2 errors, which is beyond what this code can do. So that's why you cannot correct the message, but you can detect there are some errors with the received message. And sorry.
In both of your third and the last cases, you had so the color code doesn't mean anything at the moment. Right.
Oh, the color doesn't mean anything. I just want to sort of like highlight the example so that you can see it easier.
Okay.
Yeah. So, but the interesting thing is, if you look at the original message versus the message with 2 errors, so you find that the error is what is 001100, right? So the error actually lies in the same concept. The error is actually this. It's just that you can detect the error, but you cannot correct the error. So then you might think that, okay, if that's the case, I change this as my concept leader, then I can correct these errors to become this message, right? Turns out that this is not the case, because even though you can correct this type of errors, if let's say there are some other errors with let's say you kind of like have two errors happening, even though you corrected this type of error, the other error that with two error occurring, you still won't be able to correct it. You can only detect it. So that's the idea of classical error correction in this case. So then lastly, we look back to the quantum case. So previously we studied the bflip code. Uh, basically, for if you want to encode one logical qubit into three physical qubit, so this is how you do it. So you just repeat the qubit that you want to protect three times. So in this case, if I want to protect from the bflip code, so basically I encode in 000 and 111. Last time we also studied the stabilizer generators. So the stabilizer generators for this kind of code basically is Z1, Z2, and Z1, Z3. So this is the circuit form that I showed at the very first discussion. So now we look at how quantum error correction actually works with the stabilizer formalism. So we can still study the syndrome like this, but not exactly like this. So if you still remember, if let's say the first qubit is being flipped, there is a way for us to detect through M1 and M2 by checking the parity between. Okay, in this case, the parity that I check is between the first qubit and the second qubit, and then the first qubit with the third qubit. So this corresponds to M1 and M2 over here. So if there is no bit flip occurring, basically what you will measure in M1 will be 0, what you will measure in M2 will be 0, because you are measuring the 0, 0 state, right? So then because Z1, Z2, and Z1, Z3, basically they are the stabilizer for equation 12. So that's why if you try to measure the eigenvalues, they are also +1. So it's 1, 1. So in this case, no problem. So now we consider a bit flip on the first qubit, which is x1. So then this will be flipped to 1, this will be flipped to 0. So in this case, when you try to compare between the first and the second qubit, the measurement that you get is 1 because the parity is different. So you are measuring the 1 state. So that's why M1 you get 1. So M2 is comparing between the first and the third qubit. So of course you also get 1. So in this case, for Z1, Z2, if we try to look at the eigenvalues, uh, because you already changed the first qubit, so the kind of eigenvalues that you have is -1. Over here is also -1. So if you have big flip at the second qubit, so you get -1, 1, and then the measuring is accordingly like this. And then for x3, it will be something like this. So the reason why there is a -1 or +1 is actually because of this. Later on, I will explain. But a few things to note here is that if let's say you have Pauli matrices at different sites, basically they commute. And if you have Pauli matrices at the same site, they anti-commute. And the second thing that we need to know is that whatever generators that we define over here, they always commute within each other. So if you try to do Z1, Z2, the commutator of Z1, Z2, Z1, Z3, you find that it's always zero in this case. So if let's say you have some errors occurring, which I label as psi e, if your error anti-commutes with the stabilizer generators, so let's say this is the beginning part, so you can extract out the error, and then because it anti-commutes, so you get a minus sign, and then you put it inside that. So you see that your stabilizer actually gets to the -1 eigenstate of your error state. However, if it commutes with your stabilizer generator, you get back to the +1. And equation 14 actually is reasonable because if it commutes with your stabilizer generator, meaning that the error by itself is inside the stabilizer group. So that's why whenever you have this kind of errors, you cannot detect it. What you can detect is always the one with the -1 sign. So that's why by this table, you can already sort of like see what type of error already occurred and what what kind of fix that you need to apply to your codes. So this is what I mean by syndrome. It's a pattern that allows you to identify what errors has occurred. So this is a basic code. And then we also mentioned last time that the shell code basically is the concatenation of the basic code and the face flip code. So if you look at this diagram, basically this is the bit flip part, and then this is the face flip part. So then for the bit flip part, we are comparing between Z1, Z2, Z1, Z3, and then Z4, Z5. So the fourth qubit and the fifth qubit, and then the second one will be the fourth qubit with the sixth qubit, and then the seventh qubit and the eighth qubit, seventh qubit and the ninth qubit. So this part covers your bit flip part. And then over here, this is your face flip part. So your face flip part, basically, when you take one comparison, you're actually comparing three qubits. So that's why you're comparing the first three, 1, 2, 3, and then the second three, 4, 5, 6. And then you're comparing the first three, 1, 2, 3, and the last three, which is 7, 8, 9. So that's how you see the stabilizer elements. So this will allow us to actually detect either a B flip or face flip. Whereas for this one, you can only detect the flip part. So for the quantum codes, for classical codes, we use one square bracket. For quantum codes, we use double square bracket. So we are protecting one qubit with 9 qubits, and then the distance, minimum distance is 3. So basically that's cover like all the basic stuff about error corrections that we need before we go into other types of error corrections. That's my last slide.
Yeah. I suppose you open for questions.
Yeah.
So your previous slide,
Mm-hmm.
one for the other one, another one. So the one that you call this, so essentially the cosets are given by the first column.
Uh,
How do you think in comparison with the one that you have shown on?
in this case, I actually haven't thought about this kind of idea. I I'm not
Okay.
I'm not so sure whether we can define this. I'm not so sure whether we can define like the classical correction like this or not.
Okay. Any other questions from anyone else? Or should I turn off the recording? Maybe then you can blast any questions.
All right.
So I'll turn the recording off if I know how. Okay, I'll stop the recording now.
All right.